So most of it was abstract, but one thing we saw was that all representations of SUN can be understood in terms of objects like this, Ferrer's diagrams. We also wrote out some formula for the dimension of these representations. Of course, I did not prove that this is irreducible or whatever. So, but I mean you have to take it as a theorem that these are irreducible representations, that is part of a math course or whatever. And so the thing is that, but there is something which you can do explicitly, since we SU2 is too simple, too trivial actually. So SU3 is the first non-trivial, and so we saw that we could choose for SU3, the Lie algebra SU3, we chose the TAs to be half of the Gelman matrices. Okay. So so now the thing is, obviously we can go ahead and do the tensor product. So if you said the analog of 3 tensor 3 can be realized by just taking the tensor product of these matrices TA, T tensor. Okay, so this will be a 9 by 9 matrix, because these are all 3 by 3 matrices. Okay, there is a little bit of a pain to do it by hand. So what you can do is to use programs like Maxima or Mathematica, and actually implement this by hand and do the symmetrization, anti-symmetrization by hand, and convince yourself that you actually can make it into block diagonal, and this decomposition actually works. It is actually fun to see. So I will give you the commands in, I just use the internet to check what are the commands for these things. The direct product of matrices is also called the Kronecker product. So that is why, so you go to Maxima, and if you give any two matrices, it will give you its Kronecker product or the direct product of the matrices. The reason I am suggesting something like Maxima is that it is freely available. Okay, but if you have access to Mathematica, the same thing is called Kronecker product. Okay, so I am not suggesting that you go ahead and do these things by hand. It's not fun, because if you see your A runs over 8, you think so. There's 8 into 8, 64 such guys, and then you have and each will become a 9 by 9 matrix. But if you do it via the symbolic programming languages, which is available, freely available these days, you can actually play with these things and explicitly see for yourself how it works. Okay, I have never done this, so it was a thought which occurred to me. So at least the least you could do is, what were the things we showed? 3 tensor 3 is equal to what was this equal to? 3 bar plus 6, right? And what was a 3 bar was this, and this was this. We also worked out 3 tensor 3 bar, and that was the easiest, 8 tensor 1. So 8 was this, and this is just a dot. And so these two are easy to do. Little bit of a pain to do is the next one, which I will write. That's if you have the 3 tensor 3, which was can someone remind me what that was? Yeah, okay. So that was 10 plus 8 plus 8 plus 1. Okay, so these were just these. This was just a dot, and this is okay. So what we are going to do today is to use all these things in explicit application, as in an explicit application is more like it. But before that, 2 lectures ago we did something totally abstract. We said, what are the labels that you would associate to a representation, and that was determined by looking at the generators and asking what is a maximal commuting set. So the Cartan subalgebra for SU3 consisted of two generators. It was rank 2, so it is rank 2, which is just a number of, and we were going to work with the convention whether it was T3 and T8, and to connect up with our particle physics application which we are going to look at, I will just define y, which is 2 by root 3 of T8. Okay. So this is so we will, so in other words, label vectors, I mean elements of an irrep V by two numbers T3 and y. Okay. I'll combine this combination and I'll call it mu. Okay. Since there are so any element will be given two such numbers, okay, and because it is rank 2. So just to make a comment in the general case, if it is rank n, there will be so as many elements in the Cartan sub, there will be n such elements, so the vector will be n dimensional. Okay. So this has a name, this is called a weight vector. Okay. So what I am going to do now is to take an example okay. So the easiest one would be just asking in the 3 representation, in the representation box, the vector space has 3 elements, right, which we will write as V1, V2, V3, and so the question is how does T3 act. Can you people remind me what T3 is? T3 was just 1 half of this, right, 1 minus 1 0, and what was T8? 1 1 minus 2 and 1 over 2 root 3. So if it becomes 1/3, sorry it is 1 by 2 root 3, is it? T8. So then y would be 1/3 of this. So what this implies is the first element has so V1 has weight half 1/3, V2 has weight minus half 1/3, and V3 has weight 0 minus 2/3. What? It does not matter, right. I can even take any linear I need 2 linearly independent labels, and the reason one simple reason is that at least the square root of 3 goes away. Okay, but the reason to choose y is got to do with historical, there are historical reasons. So in mathematical literature you would not, I do not think people would choose y, they would choose T3 and T8 itself, it is good enough. Okay, there is no, I mean you do not lose anything, right, by how you specify things. Okay. So this is what you get. Now the question is what about these representations, say this 3 bar is kind of very easy. okay. 3 bar and 3 will they have the same weights, yeah, there is no complex in these things, so they have the same weights, okay. Now, but we would like to ask what about the 6 for instance, or for instance what about the 8, okay. So in fact 8 is as we already saw that the adjoint representation is very natural, it is actually related closely to the Lie algebra, and so for the 8 there is a nice way of understanding it, it is just the you take for the adjoint representation you have to just look at the eigen T3 with any element. So T3 with say some element like T3 of Ta will be some actually will be up to a sign which I am not sure what is I mean up to a sign this will give you. So, so the statement in the adjoint representation is equivalent to this commutation relation, okay. Already we saw some inkling of this in one of our assignments. So, so for the adjoint representation which is in the 8 you can see that these are just the eigen values of this, okay. So you can, so one way of doing that is to just now going back to working out looking at the Lie algebra of SU3 and you can extract out these two numbers, okay. If you find that something is not in if the way it was written it was not in an eigen state, then you have to take linear combinations and make it. So for instance obviously T1 and T2 are not eigen states of T3, but T1 plus or minus I T3 T2 would be eigen values, okay. So there is some so you will need some change of basis. So let us put that after a suitable change of basis, because if you looked at T3 T2 you will get T1 here, okay. That is not quite it is not an eigen this thing. So but you can you can always find the suitable linear change of basis such that this is true, okay. So now I am out here I have written out so what you can see is that so one more thing you can see here is T3 with T3 is 0, okay, and Y with T3 is also 0. So the eigenvalue for the weight vector for the Cartan elements of the Cartan subalgebra in this case T3 and Y is 0 0, okay. It does it. So the point one more thing which you can see is that you can have elements in a representation which have the same weight vector, okay. But there is a notion of a highest weight or a lowest weight vector which is like our bottom and ceiling which we talked about, those tend to be unique, okay. I use the word highest weight vector without ever defining what highest meant, okay. So highest or lowest again that is a point of view, right. If you stand on your head higher I mean up becomes down, down becomes, so those kind of things it is just sometimes it is just a convention, okay. So let us look at what happens in the 8 dimensional representation which is the adjoint, okay. So what you will find is I like to always look at it in the following way. We know that T3 T1 and T2 form a SU2 subalgebra, okay. So if you keep track of the T3 eigenvalues, if you just this thing, then what you will see is that if you know what the it is just an SU2, so you just need to know what spin multiplet it is. So I will look at this thing and I will do it in that fashion, okay. So let us look here and see this. So what we see here is a half and a minus half. So this is a spin half if you looked at the SU2 subalgebra given by T3 T1 and T2. So this is spin half, this is spin 1 minus 1 0 and plus 1, and this is again a spin half, okay. The y eigen, they differ in y eigenvalues obviously, and this point actually even though I have indicated by one dot I actually should put two dots, both are on top of each other. So I am just drawing it because, okay, and there is also one guy which is a spin 0, which is independent of this thing. So you can see that if you just looked at it as decomposition, so what we are seeing is the statement I am making can be understood in this form: 8 of SU3 decomposes into, looking at this particular SU2 subalgebra, into 2 spin 1s. Okay, so 2 copies of J equal T3 equal to half, no, let us just write it as 2 copies of spin half representation, right, plus 1 copy of spin 1 let me write spin. So what we have is 8 is breaks up into 2 copies of spin half plus 1 copy of spin 1 times plus sorry 1 copy of spin 0. Okay. And there is also this 10, which is the symmetric guy, and that is forms a decouplet, and you can see how that's kind of very nice. It's 1 copy of spin 3 half, spin 1 wait was 3 half, 1 half and 0. Similarly 10 equal to okay. So this picture tells you a lot more than that. It also gives you the y eigenvalue, but it is useful to look at it one by one. Okay. So now let us look at the y eigenvalues, and we see that in the spin 8 there are 4 guys with y equal to 0, and 2 with y equal to plus 1, and 2 with y equal to minus 1. And you can see the reason I have to only go horizontally, you might think can I have some weird thing like can I have one here somewhere else which can form a SU2 multiplet. That is not quite true, because y commutes with T3, so you can simultaneously diagonalize them. So in other words, if you take an so if something is in a given representation of this thing, it's all of them will have the same y eigenvalues. So that is why I am going, I am just looking, I do not even have to look very far, I just say okay, I take these two have to be paired up, okay, because we are looking at this. Okay. If you go to higher representation, there might be many ways of decomposing, then you need to put in some work, but here there is no ambiguity out here. Okay. So these pictures hopefully make sense from the abstract viewpoint. Okay. So this is obviously called the octet, and this is called the decouplet. Okay. So are there any questions? So what I am going to do now is to put all these things together and use it in what is called the Quark model. So I will spend about 5 minutes telling you about the Quark model. So first thing is that particles in nature, by that I mean fundamental particles, okay, so are broken up into 2 kinds of things. We will call things which we will call hadrons and things we will call leptons. This so first thing is that actually first what you do is to distinguish between bosons and fermions, and all the bosons that we know of, like photon, W and Z bosons, they are all they transmit, they are carriers of some force. The exchange of them gives you various forces in nature. So we know, so when I mean particles, I mean things which are constructed from fermions. Okay. So the thing is that the leptons do not feel what is called the strong force. This is what keeps the nucleus together. So you can't, I mean you cannot have protons together because they are both positive charge and without any, so there must be something which cancels the electromagnetic repulsion, okay. And so people conjectured there is this strong force which is attractive and which cancels this thing. But then you may say, why is it we do not see this thing, and the answer to that is that it has a very finite range. So up to some distance it has an action, but if you go far enough it becomes very weak, okay. And a beautiful model for that is to think of the potential going as e power mu r upon r, where mu is some mass, okay. So you can see something like this can be this force will die off very exponentially fast when I have used mu here because in a natural units mu is like a mass, or 1 over mu is like a length scale. So at length scales greater than 1 upon mu you will find that this force will die down, okay. So this is called the Yukawa potential. And you can show in from elementary calculations in quantum field theory that you will get this kind of potential if a force carrier has mass mu, okay, and you are asking what is the potential due to one exchange, and this is what you get, okay. So it is a wonderful model, but that is not relevant for us. What is relevant to us is that there are strong forces. There are things which do not feel any strong forces. It is similar to uncharged particles not experiencing an electromagnetic force. So there are particles which do not experience the strong force, they are called leptons. Examples are electrons, muons, okay. But hadrons, they experience a strong force, so obviously examples would be proton, neutrons, etc., okay. So but they also fall into two categories called mesons and something called baryons. So these examples of these are protons and neutrons, and here examples are what are called pi mesons, pi 0, pi plus, pi minus. These were I guess first observed in cosmic rays, and then there are many more, I do not know, k 0, k plus minus, even here there are many more. And what happened is that when experimentalists started doing were carrying out experiments, they started observing what are called resonances. So if you have looked at any computation of differential cross sections in quantum mechanics or in some particle physics course, what you will see is that there will be there will be a peak as you change your energies, you will find somewhere a peak coming, okay. And usually even in a quantum mechanical problem you will see that these peaks are related to the existence of some bound state or some new or production of some new particles or what, okay. So now the thing is, in fact there is more stuff to it. The width of the resonance is related to the lifetime of the particle, okay. So particles need not so these particles can be metastable, they can decay into other channels, so they will exist only for a finite amount of time. By the way, if I have a free neutron, does anybody know its lifetime? 15 minutes. The question is, why do not we decay? We are made up of protons and neutrons, why do not we decay? So we do not have free neutrons in our body, they are bound, they are sitting inside the nucleus, okay. So that is why we do not decay. So the question is, but the thing is, what happened is that people started finding lots and lots of resonances, and there was a fight, every day you discover one, you give it a name and you name it after whomever, your dog or your wife or your girlfriend or whatever. So you could give it all sorts of names, and the question was, it's total, I mean it was more like a zoo of particles when you had this classification. That was the historical setup, and Gell-Mann and Niemann came up with this idea, or maybe these objects which we are thinking, which we see, are not fundamental particles, they actually consist of some other constituents, okay. But actually that was not the reason. First group theory was used. Gell-Mann came up with something called the eightfold way, okay. I guess this was a takeoff on Buddhism or whatever. Gell-Mann is a polyglot, he knows many languages, he knows a lot, and so it's not surprising he knows a lot about eightfold way and stuff like that. But he came up with this idea that we could organize this zoo of particles into octets, maybe decuplets, etc., and so somewhere he said no, SU3 has some role to play, and then they found that by assigning and all particles which you saw, you would assign quantum numbers to it. So quantum numbers which were assigned were obvious ones. Spin of a particle, you can ask, you know that, you would know its parity. Okay, then you could, then they started assigning other things. There was something called hypercharge, which is y, and then of course electric charge of the particle, then baryon number. Okay, so the idea was that it just distinguishes. So mesons have baryon number 0, baryons have baryon number +1, antibaryons have baryon number -1. Okay, so these kind of quantum numbers, people, I mean, they were assigned to all these particles, and what was remarkable was that Gell-Mann and Niemann are able to show that by using SU3 representation theory, they were able to relate some of these things and organize the stuff. And a little bit down the road, I mean Gell-Mann and I forget who proposed the Quark model and few others. So it led to the constituents which were called quarks. Okay, so the thing is that these were not fundamental particles. The fundamental particles were supposed to be quarks. Okay, so what were the kind of quarks? So the first thing you would like to know is what are the quarks which are in proton and neutron, etc. So first thing, they needed two quarks, u and d, up and down you could call them, and there was some more, I mean isospin. So there were, I am not writing a complete list. Okay, so you have u and d, and so people put things together, and so the neutron was supposed to be made up of one u and two d's, and a proton was supposed to be two u's and a d. Okay, and the way I remember things is that I think of neutron as the dot, it has 0 charge. Okay, so now we have to now sit down and assign electric charges to u and d such that neutron and proton have the appropriate charges. So already you can see that d should be half of u, and there will be a sign difference. So we fix that by coming here. Okay, so you will see that you will require u to be charge q of u should be I think 2/3, and q of d should be -1/3. So this is the electric charge of these guys. Okay, but the power of the Quark model is, now if you say that there is something else made up of these guys, these charges were additive and it should work out. You don't need to know details about this thing. So there are a lot of consistency checks, etc., and but then it was discovered that these two quarks weren't enough, and then they found that there was a third quark which you needed to introduce, and that was done by introducing one more, yet another quantum number called strangeness. Okay, but today we know that, I mean today we have observed up to 6 quarks, and they are u, d, there is a reason of writing, there are families or whatever, charm and strange, top and bottom, or top and beauty, or truth and beauty, depending on whom you ask or which part of the world you are in. So these are, so you have 6 such things, but there is a sense in which u and d, so if you ask in terms of what are their masses, the lightest guys are u and d, and as you keep increasing masses it goes s, c, b and t, and t is at t is like in hundreds of, it's around 150 GeV or something like that. Okay, and it's, so obviously it's very massive, it's more massive than the W boson. Okay, and it has many channels to decay. Okay, so you have so many things, but so obviously since these guys are massive, so if you are looking at low energy energies which are much lower than these the masses, rest masses quote unquote of these particles, in as much as you can observe them, but then you would need to only work with three such quarks. Okay, that is U, D and S. Okay, and if you push things you will get to C. Today we have reached a point where there are B factories. Okay, B factories are those which whose energies are so high enough to produce mesons and baryons which have bottom quark copiously. So you can see that it's taken quite a bit. We are talking of 40 years since all these things were found. Okay, so for the rest of this lecture we will assume that there are only 3 quarks, and we made a big deal about symmetry out here in this course, but actually the SU3 which we are going to discuss is called SU3 flavor. It is only an approximate symmetry. If it were really a symmetry, then first thing is you should see that U, D and S should have the same masses. They do not. They do not even have the same some other quantum numbers are not even the same. So it is a case of an approximate symmetry, but that itself was very useful bookkeeping device, and you can fit it into a much more robust thing called the standard model. That is not our this thing, but the great idea was to think of U, D and S as forming a 3 of some SU3 flavor. And the SU2 which I was talking about corresponds to looking at the subgroup which acts only in which U and D are a doublet. Okay, and this T3 actually this fits into something nicely in the standard model. To the eigenvalues of T3 become something called isospin. They get related to that, but that is not so. So this was the idea of Gell-Mann. Let us put these guys into this thing, and then the antiparticles will be in the complex conjugate representation. So we just write U bar, D bar and S bar belong to 3 bar of SU3 flavor. Okay. So now the question is, can we ask what are the constituents of mesons and baryons? Okay, so I will just these are only rules or whatever. First one is a meson consists of a quark or I can say it is a bound state of a quark and an antiquark. Okay. And a baryon is a bound state of 3 quarks. Okay. So how many such bound states can we have? It says take a 3 and a 3 bar, so we can get 9 of them, but now we want to organize them in terms of SU3 irreducible representations. This is something which we have already solved. So we get 3 into 3 bar which was equal to 8 plus 1. So it tells you that the mesons that you would find consisting of U, D and S should sit in an octet. So let me write out those things. Okay, so these are the names given to these guys, and I think when Gell-Mann made the prediction, I think eta wasn't observed or whatever. So he said you should observe it in this thing, and in fact there is a mass for even there was a formula for the masses. So what you do is a 0th order approximation, you assume that quarks and antiquarks are massless, but they have masses, okay, and you put those masses in, and if you you can sort of do it there is a very beautiful computer, I think it goes back to Nambu, where you can actually compute what the masses of these things should be. So there are in terms of some unknown quantities which you can fit by 1 or 2 masses. So there are not too many free parameters. So the parameters will be, I guess, the masses of the UDS quarks and also the strength of the binding in this thing. So with these 4 numbers you could actually give 8 masses. So that is a prediction. Okay. So one more thing is these are all these are spin half particles, they are fermions. Okay. So if you look at this, if you look in terms of spin, it is half tensor half, so it could either be 1 or a 0. Okay. And yeah, okay. So and so what I have drawn for you is the 0 octet, so it is called the 0 minus, the parity you can show is minus. Okay. So what I have drawn is the 0 minus octet of mesons. Okay. And the numbers, these are all predictions, and in fact there is a beautiful formula called the Gell-Mann-Nishijima. So I told you there are a whole bunch of quantum numbers, U1, hypercharge, strangeness S. So out here strangeness has once you understand in terms of quarks, tells you how many strange quarks are in it. Okay. For historical reasons it turns out that a strange quark has strangeness -1, okay, and a anti quark of that has strangeness +1. So I will just write out for you what the strangeness. So this contains, this turns out to be S equal to -1 and this turns out to be S equal to +1, goes in the opposite direction, does not matter. Okay. So or formulae was okay. So these were like consistency checks, because you can see now people have observed mesons, they are giving a whole bunch of numbers, and the fact that you put these things into SU3 gives you all these rules which connect up different what look like different numbers. So that is the check of this idea, okay, and it clearly passed the test. So that is with respect to the mesons. But what about octet, the octet? So we have to look at there, you have to look at 3 tensor 3 tensor 3. Okay, and this we saw broke up into 10 plus 8 plus 8 plus 8 plus how much was it, 1. Okay. So obviously there is an octet. First thing is let us do the spin part, it is half tensor half tensor half. So the maximum you can get is 3 half and then you can get half. Okay. So baryons will have either spin half or spin 3 half. Okay. So it turns out that proton neutron sit in an octet, and and we know that protons and neutrons have spin half. Okay. So protons neutrons half plus is what is written. Okay. Spin half plus particles, it tells you that the full octet has this property, not just one of them. Okay. And so these are standard in this thing, but nice thing here is that there is a decouplet coming out here. Okay. So you look at the decouplet, you find that there are this is a whole new set of things, and the decouplet again in the decouplet we will have I am just looking at the figure which I have. Okay, good. So the thing here is, yeah, let us look at something like this. It is called omega minus, I think. And so in this thing, if you start here, s is equal to here -3, s equal to -2, s equal to -1, s equal to 0. So these 4 guys are the things which do not which are made up of only up and down. They do not contain any strange quark. Okay. So if you look at this particular guy, it has s equal to -3. How would you get that? You would get it from 3 strange quarks. Okay, and let us say we are looking at the 3/2 guy, spin 3/2, that means all the spins are also lined up. So it looks as if you have an object which violates what is called the Pauli exclusion principle. All quantum numbers are the same, s s s. So you have to anti-symmetrize, etc. If everything is the same, you will get 0. Okay, existence of something like this sort of was a puzzle, and the resolution was done in the following way. The resolution was that that there exists some other quantum number. Okay, there exists another quantum number called color. Okay, so which we have not seen out here. So add a new quantum number. Now let me write it somewhere else. Called color. Okay. So in other words, so the minimum number you would require is at least 3. Okay. So in other words, it can take so there can be yeah. So the but it is better if that includes what happens there is that the extra quantum number is another SU3. So if you take fundamental of SU3, if you say that the quarks are in the fundamental of SU3, then it will have another quantum number. There will be 3 such numbers. So then you can see that I can choose, even though it's like the spins are all lined up, it's maximum 3/2. I can construct that guy such that these things all line up, but the other quantum numbers I can anti-symmetrize in that sector. Okay. So and Pauli's exclusion principle is not valid, but the nice thing is that this SU3 is a local SU3. Okay, and people usually put a C out here, and this local SU3 implies that you will have how many gauge bosons? Implies you will have 8 new no, we shouldn't call it new gauge bosons. Called gluons. Okay. So now you can see that if you look at the strong sector, we see that first in terms of fermions there are new particles called quarks, and then there are also 8 gauge bosons which are called gluons. Okay, and these are supposed to be carriers of the strong force in some sense. Okay. So if you combine all these the idea of the quark model plus the idea of having color, you find that you need, so the prediction should see quarks at least 3 quarks, okay, quarks and gluons. Okay, puzzle. Is that actually no, we never observe free particles that carry color quantum numbers. Actually color representation is the correct. I don't want to call it color, I don't want to call color as a quantum number, because it is not something like charge which is additive, it is a non-abelian gauge group, we know that thing. So it is more like the representation, so it should be in some representation. And okay, so we said, for instance, use U, D, S and all other quarks belong to 3C. So the subscript here is to remind you that it is color 3. Okay. This combination also, I mean, by that I mean each one, U belongs to 3C, D belongs to 3C, S belongs to 3C, so on and so forth. Okay, it is different from saying put UDS as a multiplet and belongs to 3 flavor. Okay. And U bar, of course, U bar, D bar, S bar, whatever, also will belong to 3 bar C or whatever. Okay. And gluons belongs to the 8, it is in the adjoint. Okay. So the whole point here is that we cannot see this thing. Okay. So what happens, so the thing is, what we see are objects like protons, neutrons, pions, etc., mesons, which actually do not seem to carry any color, because we saw that with this whole discussion we never needed to discuss anything called color. Okay. And you could ask, can it be SU2, can it be SU3, can it, why not SU4, why not SU5, so on and so forth. All these things are issues, but which cannot be decided in a room, but are they lead to predictions of some other experiments, and that will be discussed in your high energy physics course. And so that tells you that that you require SU3 will do. Okay. But there is a theoretical issue, why is color not observed. So this leads to something called the idea of color confinement. So just to contrast things, what we do is first look at electric object which carries electric charge. Okay. So if you have something like this, it has lines of force which sort of spread out in all directions, and if you did some integral flux computation, you will get some charge. Okay. So this is for electric. So let us put electron or something electric. Okay. But if you consider color charge, what happens is something quite interesting. So let us say, let us put an electron here, we put Q for a quark here. What you find is that it's energetically favorable for all the flux lines to get sort of bunched up into a tube. Okay. So you end up with a flux tube, okay, which could go and end at a, for instance, it could end at a quark bar. So this would be the model of a meson if you try to pull it, but remember it has finite, I mean the strong force has finite range, etc. So what happens is, if you try to pull, separate them further, I mean this is only a theoretical experiment. Okay. If you try to pull them, it is sort of favorable for this to snap here, because this has some energy density. So the energy, or you can think of it as a string tension. So T times length will be the energy. So as you increase the thing, the energy keeps of that thing is increasing. At some point it is favorable for it to break, to form quark anti-quark pair out of vacuum, no quantum numbers are violated, nothing. So you can break this and you can end up with Q, Q bar, Q, Q bar. Okay. So so this is so this idea that that color flux has to be confined, this is what happens. Okay. So in other words, you will never, I mean the idea here in pulling this apart was to see, can I create a free quark. So I have what I have done here is sort of considered a meson which has a quark and an anti-quark, and try to pull them apart by smashing something or whatever, does not matter, but the idea is, can we separate them, and this is what happens. And this sort of this captures the problem in, or solves this puzzle, that this cannot happen. And theoretically in quantum field theory you can show you can start with a theory which has free quarks and free this thing, and you see that what you see is that it goes to strong coupling if you come to lower and lower energies, you find that the coupling constant which binds things together keeps becoming stronger. So at low energies, which is what we are pursuing, we are not looking at things at high energies. What we would see is only objects which are color singlets and nothing else. So now you might ask, what happens in the accelerators? There we go ahead and smash things and pull them apart, and there you can actually do things. You will reach regions where you will actually produce quarks, antiquarks for brief amounts of things, and again what will happen is precisely these sort of things. I mean, as they start decaying and losing energy, they will end up at the end being colorless objects. That is what you would see, but you end up seeing jets. So people have now, experimentalists are really clever. They have reached a point where they can tag objects and say, hey, this is a U, this is a D, this is a C, this is so on and so forth. They are really very, very clever. I mean, they have signatures of how each of these things decay, and it is sort of there is some theoretical backing to it, but it is more like there is certain art also in that thing, not just science. And so people have reached a point where they can identify, okay, this is a gluon shower, etc. Okay. So this part of this thing is called the what is it called? It's called SU3 color or whatever. So I will stop here.